A farmer claims that the average weight of his melons is 6 pounds. A random sample of 50 of this farmer's melons has a mean of 5.4 pounds and a standard deviation of 0.9 pounds. Use a 5% significance level to test the claim. Provide the practical outcome of the test. Okay, so they're asking us to test a hypothesis, right? And so that's clear, I think, here from this phrase, test the claim. So let's go ahead and write down the claim. That's our very first step. So sort of step one of the process, identify what the claim is. And the claim here is that the average weight of this farmer's melons is 6 pounds. So they're saying the mean is equal to 6. Now from there we want to identify the null hypothesis and the alternative hypothesis. And that's pretty easy once we have the claim. So because the claim uses an equal to sign, it will be the same as the null hypothesis because that's one of its symbols. And then the alternative must express the opposite idea. So the opposite of equal to is not equal to. And so there we have the claim and the two competing hypotheses. Now we need to get some data together so we can form a test statistic. So we're going to copy down the data from the problem. We'll figure out usually that we need a sample size, a sample mean, some kind of a standard deviation, and then we need a significance level. So let's try to identify all those items. So it looks like they have a random sample of 50 melons, so n is 50. Looks like the sample mean was 5.4 for that group of melons. So a little under what the farmer promised, but of course there is going to be some natural fluctuation. That doesn't mean that the farmer is wrong. Standard deviation of 0.9 pounds, 0.9, right, is the standard deviation. And then a 5% significance level, that's your alpha, so 0.05, and that's pretty typical as a choice of alpha. Now from here we need to come up with a test statistic. So when doing the test stat, we basically have to use the following formula. We'll use z equals to x bar minus mu sub 0 divided by the standard deviation over the square root of n. Now, a little note about z, we're going to use z here because that sample size is nice and large. It's over 30, so we can safely use z, I think. Okay, now from here, we're going to say that z is equal to the sample mean we have to the left there. It's 5.4. Where do we get this value from? Remember, it comes right from the null hypothesis, right? That little subscript of 0 there is telling you take it from the null. Take the value 6 then, and divide by the standard deviation. We're going to use the s as a substitute for the population value, and then divide by the square root of n. In this case, n is 50, right? Okay, so now we have our z test stat. We need to work that out and see what it gives us. So go ahead and open up a parentheses, do 5.4 minus 6, right? Close up the parentheses, then divide by, open parentheses, 0.9 or just 0.9 divided by the square root of 50. Close up the square root, close up the parenthesis, press enter, and you get minus 4.71. Minus 4.71. Okay, so that's a pretty extreme z-score. I want you to kind of get in the mindset that when your test stat is extreme like that, you're most likely going to reject the null hypothesis. But the way we confirm that is to use a critical value. If we're doing the traditional method of hypothesis testing, we're going to now need a critical value and a rejection region, right? So the critical value can be found by first determining what type of test you're dealing with. So when I look over at HA, I say, okay, wow, that indicates a two-tailed test because the not equal to sign, right? Not equal to sign means a two-tailed test. So we're going to have sort of a two-sided rejection region, right? We'll have a rejection region over here and one over here. And that means that my significance level, my alpha, has to be split among two tails. So this is the only time I divide alpha in half. So I'll say that this isn't 5%, but rather it's half of 5%, which is 0.025, and that would be the same for this side as well, 0.025. And we can figure out 0.025 in one tail by looking at the t-table and going down to the bottom where they have z-scores. So let's go look up 0.025 on the t-table. So here we are on the t-table, an area in one tail, 0.025. Go straight to the bottom, we'll get the z-score, and we should be using a z-score here because, again, the sample size is large. And we have 1.96 as the critical value. That means a plus and minus 1.96 because we have two sides, right? So 1.96 on this side, but negative 1.96 on the other side. And essentially on this z number line that we have drawn, where does the test stat land? And this is the way we form our initial conclusion, right? So our initial conclusion. Okay, well this test stat definitely lands over here, right? Somewhere over here on the number line. And that would be definitely well into the rejection region there on the left. So we're going to go ahead and say that we reject the null hypothesis in this case. So we reject the null hypothesis. Now whenever you reject the null hypothesis, what goes hand in hand with that is that you support the alternative hypothesis. And the reason why is that these are in competition with each other. So if you're saying, hey, reject HO, you're basically saying that HO can't be trusted anymore, that the evidence seems to indicate HO is false. And that means that we should therefore support the alternative because it's saying the opposite thing, right? So if you're throwing out HO, you must be supporting HA. But the question is, which one should we use in our wording, right? Well, if you look at the claim itself, the claim in this particular problem was the same as the null hypothesis. So we better say this then. We should use something that says we reject the claim. So we're going to say, hey, the sample data allows us to reject, right? Allows us to reject the claim. And you could reword the claim in there. You can say the claim that the melons are 6 pounds, right? I'll just say ... because you can fill in that yourself. But the practical outcome of the test is this, that basically the evidence we have that we gathered, that set of sample data, those 50 melons we took, that set of data strongly indicates that the true weight of the melons is not 6 pounds. That's essentially what we're saying, right? Because we're saying, hey, the farmer said it was 6 pounds and our data came in a little bit less than that, 5.4 pounds. You may say, well, that's not too far away from 6. True, but because of our sample size being 50 and because of the small standard deviation, right, that was enough of a difference for us to be able to say or show that the true weight seems to be something that's under 6 pounds. And I say under because the sample mean was 5.4, right? And if we reject the null hypothesis that said it was equal to 6 pounds, then most likely it's because the true weight is less than 6 pounds. So the practical interpretation here is that most likely the farmer is sort of inflating the weight of his melons, or he's mistaken about what the average weight of the melons is. Now, of course, there is the possibility that we made a mistake, right? That our conclusion is actually not correct. And that's basically, in this case, the possibility of a type 1 error, right? And if you want to know the probability of that, you can listen to some of the other slides or videos that we have, but I will just tell you that the probability of a type 1 error in this particular case will be equal to alpha. So there's only about a 5% chance that we just made that mistake of a type 1 error. And a type 1 error, again, is the idea that we rejected a true null hypothesis. So we just rejected the null hypothesis, right? So there's always a possibility that we just committed a type 1 error because if you reject a null hypothesis that's actually true, you commit the type 1 error. So there's a chance of that, and the actual chance is just 5% here, so it's not too likely.